To Perspectives on Bayesian Statistics in the Life Sciences, Kroisu Isaf Punchai are Istadigai, Bayesaif, and Gogorai Boyd. I'm David. Most of you know me. I've organized this event together with Anna, and this afternoon is the first part of a 2 days event series devoted to the role of Bayesian statistics in the life sciences. I'm delighted to say that we look forward to 2 great talks today and a discussion. And tomorrow this will be followed up by a practical workshop with Richard on practical implications and modeling with Bayesian statistics. Also want to say that it's great to see so much interest. We have had more than 120 sign-ups for this event today and tomorrow together. And before introducing today's first speaker, we would also like to thank the Doctoral Academy for the generous support that allowed us to invite Professor Stephen Senn from the Institute of Health in Luxembourg and Professor Michael Goldstein from the University of Durham to Cardiff for today. Also, we'd like to thank everyone who has supported this event, and in particular Dr. Richard Morey, who has been the patron of this project, as well as Dr. Carrie Wallace for designing the flyer. Personally want to thank Anna, who is helping with the organization of the workshop, but also created the website, cardiffbayes.wordpress.com. And we will record both lectures today and put the lectures as well as the material of Richard's workshop tomorrow on the website, so you can access it later offline. So now it's my great pleasure to introduce today's first speaker to you, Professor Stephen Senn. Stephen Senn is an expert in clinical trials and professor at the Luxembourg Institute of Health, where he leads the Competence Center for Methodology and Statistics. He has previously worked for the NHS in England and also advised the Swiss pharmaceutical industry before becoming professor at UCL and Glasgow University. Stephen has authored 3 books on statistics in clinical trials and in medical decision making. He has been awarded numerous prizes, among which was the Bradford Hill Medal of the Royal Statistical Society in 2009. But his proudest professional achievement is having led the Royal Statistical Society team that reached the finals of University Challenge, the Professionals, in 2006.
We were beaten by a bunch of librarians.
Maybe just a bit of housekeeping. After this introduction, Richard is going to tell you a bit more about this workshop, and then Stephen will start with the first talk, which addresses p-value wars. After Stephen's talk, we'll have a 50-minute break in the foyer with biscuits and coffee. And then we will resume here at 4:15 sharp for Michael's talk, which will be addressing Bayesian uncertainty quantification for complex systems modeled by computer simulators. You are after that also invited to stay for the open discussion we'll have, and which will be moderated by Richard. And without further ado, I hand now over to Richard, who will explain a bit more about perspectives on Bayesian statistics in the life sciences. Thank you.
Hey everybody. I probably know a lot of you, and a lot of you probably know me, so I won't say too much about who I am. I'm a senior lecturer over in the psychology department. And I wanted to tell you a bit about why I worked with David to invite the speakers that we invited. So tomorrow I'm going to give a workshop on applied Bayesian statistics, how you do it, what Markov chain Monte Carlo is, all of this stuff. And it's fun to give this workshop because there's a lot of enthusiasm about Bayesian statistics currently in a lot of the sciences. But with this enthusiasm comes a certain amount of danger that people stop being critical of these particular statistical methods. And so what I wanted to do was to provide a sort of counterweight or a context to the workshop that I'll be doing tomorrow, so that I can keep everybody sort of healthy skeptics about the methods that they use. So that was my idea, and I hope that it works. And I'm really looking forward to both of the talks. So yeah, that's all I wanted to say. So I guess I'll hand it over to Stephen. Let's put your talk up.
Well, first of all, I'd like to thank Richard and David for the invitation, and it's a great pleasure to be here. It's quite a while since I've been in Wales. Secondly, I'd like to acknowledge the support that the European Union has given for the particular work that I do on rare diseases, which is sort of somewhat behind the particular inspiration I have to defend standards of evidence that statisticians use. So this is the outline of my talk. I'm going to give you some basics. I'm going to describe, first of all, the difference between probability and statistics. I think it's very important to understand this particular difference. Then I'm going to give you an example. Then I'm going to give you some recent criticisms of p-values and significance tests. John Ioannidis is an iconoclastic epidemiologist based in Stanford, and he's been writing a lot of papers in which he's been criticizing a common frequentist approach to statistics. I'm then going to say something briefly about replicate, which is a particular controversy which has erupted in psychology, which I'll say something about the ASA statement, the American Statistical Association statement on p-values. Then I'm going to give you a brief history of p-values in order to explain that, in my opinion, the problem and the fuss is not quite what people think it is. I think if you understand the history, you'll see why that's the case, and then offer you some conclusions. So, basics. So, what is the difference between probabilists and statisticians? Well, the first thing to understand is that probabilists are really mathematicians. They deal with direct probability statements. Essentially, they deal with a formal game, and they're involved in the divine. Basically, God knows what the probabilities are. It's not the job of the probabilist to say what they are. It's simply the job of the probabilist to calculate some consequences of the way in which God has created the world. Statisticians are much humbler people. They are scientists, and they deal with inverse probability problems, at least. And they deal with the real world. And they're involved in the human. So basically, we're down here. We're not privileged to know what the mind of God is. We're trying to work out what the mind of God is based on the evidence that is around us in the world. So to give you a concrete example, here's an example of probability theory, a very trivial one. The die is fair. What is the probability I will get 2 6s in 2 rolls of the die? If I can assume that they're rolled in a way which is completely independent, then a plausible argument that many would agree with is that the probability is 1/6 squared, which is equal to 1 over 36. Not a particularly controversial calculation. That's a probability calculation. Now let's produce a statistical one. I rolled this die twice, and I got 2 6s. What is the probability that the die is fair? And the answer here is nobody knows. Or at least if they do know, then in that case, whatever the answer they come up with will not be the same as yours, will not be the same as a neighbour's, or whatever. So this is the basic problem. The first question is inherently easy to answer, and the second question is inherently difficult. And I maintain that probability theory is an inherently easy theory compared to statistical theory. This doesn't mean that probabilists are not doing more difficult work. In fact, many of the sort of things that probabilists have done have been extremely deep and extremely difficult. I'm just saying that inherently it's an easier problem than the reverse problem. So, probability statements are not reversible. That's the first thing to understand. Is the Pope a Catholic? Yes, I think so. I think it's probably the case that Pope Francis is a Catholic. Is a Catholic the Pope? Probably not. If you choose a random Catholic, then the chances are he's not the Pope, or he or she is not the Pope. And it's important to understand that this applies to all sorts of things. The probability of the evidence given the hypothesis is not the same as the probability of the hypothesis given the evidence. So the probability of getting 2 6s if the die is fair is not the same as the probability that the die is fair given that you've seen 2 6s. These are fundamentally different things. And this particular point is often overlooked by people, and we very easily, even experienced statisticians, can fall into the step of mistaking one for the other. So how would one go about producing a solution to this die is fair or not question? Well, if you're a Bayesian, you could state a prior probability for every possible degree of bias in the die. You could perhaps produce some model for it, or think about it and say, well, I think it would be biased a little bit. After all, we create a die by burning holes in the faces of the die, and it's not going to be perfectly balanced, and so maybe something like a 6 is a bit more likely to come up than a 1, which is on the opposite side. We could start thinking about this particular way. We could produce some sort of prior probability model, and then what we could do is we could calculate the likelihood, which is to say the probability of observing 2 6s given every particular probability of a single 6. And then we can use Bayes' theorem in a way in which I will explain to you with an example to try and produce a posterior probability. What the frequentist does is he assumes the die is fair, then calculates the probability of the result on the assumption the die is fair, and then if it's low says, well, now it's up to you. What I can tell you is something rather low of low probability has happened. Either you think that the hypothesis that the die is fair is true and this low probability event has happened, or you begin to believe that maybe the die is not fair. And basically, the frequentist will then wash his or her hands of the problem and say it's over to you. So now I'm going to give you a practical example. This is an example which is in my book, Statistical Issues in Drug Development, and it dates from an era in which it was thought that the CD player was actually a revolutionary bit of progress in terms of home entertainment. You're all too young to remember this, but prior, yes, there was something prior to a CD player. There was, in fact, vinyl. There was a record player, and used to put a record player, a plastic record, a vinyl record, on a turntable. And my kids, when they saw this demonstrated once, couldn't believe it. They thought it was absolutely incredible. But anyway, I still had one some years ago. But this was a CD player. At the time, it was fairly new sort of thing, sometime in the early 90s. And I was playing the CD Hysteria by Def Leppard. For those of you who don't know it, Def Leppard are a heavy metal band, and it's sort of inherent to white males of my particular generation, the sort of music we tend to play when we're not careful. So I was playing the CD Hysteria by Def Leppard, and it's got 12 tracks. And I sort of used to like to surprise myself, not to know what the next track would be, and so I pressed, as I thought I'd pressed the shuffle button. And in fact, the track that was then played was the first track on the CD, which for those of you who are not familiar with Def Leppard's oeuvre, is in fact Women. That's the first track on the Hysteria CD. And so I said to myself, aha, evidence that is compatible with two possible hypotheses. Did I press the shuffle button after all, or did I press the play button? This is the way the mind of a statistician works, by the way. I now have an iPod Nano. But anyway, so I then asked myself this particular question. So what I'm now going to try and illustrate to you is how a Bayesian would answer this question, first of all, and then say how a frequentist would. So we've got two basic hypotheses. I press shuffle, I press play, and the first thing we have to do is to establish a so-called prior probability for these hypotheses. And when I ask my students what it should be, they sometimes very hurtfully say 1/2. Why hurtfully? Because their professor has told them that he intended to press the shuffle button. And if they think that when he intends to do something as simple as that his probability of getting it right is only 1/2, the opinion they have of his abilities is not very flattering. On the other hand, I can't say that I devoted much attention to doing this. I sort of leant over and pressed the button. And so I'm prepared to give myself a 9 out of 10 probability of getting this right only. The point here is at this particular stage, you're free to posit any number you like. You've already got a little bit of evidence of my competence and ability as a human being. You can make your own particular assessment of what it will be, but I suggest that it will make this lecture a lot easier if you accept the one I've made. Otherwise, you're going to have to do all the other calculations in your head from now on. So let's, for argument's sake, accept that I have a 9 out of 10 chance of getting it right. The probability of making a mistake and pressing the play button is then 1 over 10. I'm then going to make another assumption. I'm going to assume that Sony, that created the CD player, created it in such a way that it would sample all the tracks equally. Might not be the case. It might have been that longer tracks were more likely to be chosen, for example. Possibility. I'm going to assume that there are 12 tracks on the CD, and each one has a 1 in 12 chance of being chosen if the null hypothesis is true. And so the probability that Women will be played if I press shuffle is 1 in 12, and this is what is sometimes referred to as a likelihood. If I press play, then the likelihood is 1, unless I got jam on the CD or it was scratched in some way and it jumped, but I'm going to assume that's not possible. So it's 1/12 under the shuffle hypothesis and 1 under the play hypothesis. For completeness, but it's not actually necessary for solution, I'm going to consider likelihoods had any other evidence occurred. Actually, as a Bayesian, you don't need to do this. Had some other track been played, say x, then the probability of x under shuffle is 11 over 12, and under play, it's 0. So that's only a theoretical occurrence. So I can put this together as follows. I put together a table which shows you the 4 combinations of the 2 hypotheses and the 2 types of evidence. So I press shuffle or I press play, I heard W or I heard X. And if I put these together and I multiply the prior probability by the likelihood and I add them up, then in that case it comes to 1. And this has to be the case because in advance of having heard the evidence, these 4 combinations are mutually exclusive and mutually exhaustive, and that means the probabilities assigned to them must add up to 1. However, I now have some evidence. So I can now strike out 2 of the rows, and I can strike them out because it hadn't happened. It's a matter of pure deduction that this didn't happen. I didn't hear it. And so now I'm left with 2 particular combinations of prior probability and likelihood, which sum to 21 over 120. No longer to 120 over 120, but I know that they represent all there is to know about the world. So what I now do is I renormalize. I simply divide by the total probability to obtain the posterior probabilities. So I simply divide by this total 21 over 120, and I then obtain the answers on the right-hand side, and it now turns out that the posterior probability that I press shuffle is no longer 1 out of 10, but it's now 9 out of 21. People sometimes ask me, but what did you do, Stephen? And the answer is, I don't know. So here is a deductive question for you. You can answer this as a matter of pure deductive logic. Since I don't know which I have pressed, what happened next? Well, the answer is that I heard the second track on the CD. And then I heard the third, and then I heard the fourth, and then I heard the fifth, and I heard them all the way through to the 12th track in the order in which they appear on the CD. And that means that formally, I don't know whether I pressed the shuffle button or the play button, but I have a very strong opinion that I almost certainly pressed the play button, and that will come out if you do the calculation the Bayesian way. So, on the other hand, the frequentist solution is simply to say, well, there's a 1 in 12 chance that that would happen if you press the shuffle button, assuming I just stopped by having heard 1 track and not had all the evidence. That is not a particularly unlikely event, so it's up to you now whether you choose to reject the null hypothesis or not. For practical applications, every result is unlikely for many practical applications. Suppose, for example, I'm looking at the effect of a particular treatment on blood pressure or on, let's say, on forced expiratory volume in 1 second in asthma. Then a particular result I might postulate that it changes the blood pressure by 9.83567 millimeters of mercury has effectively a probability of 0. And any particular precise value I would nominate has a probability of 0. So all events in advance of actually studying them are of low probability, and so this idea of rejecting a null hypothesis simply because the probability is low doesn't survive. And instead, what we do is we nominate events as extreme or more extreme than the event observed. So if I see a particular difference between 2 treatments, and I say, well, that particular difference or a more extreme difference would be unlikely to occur if it were the case that the 2 treatments were the same, then in that case I use this particular probability of an event as extreme or more extreme as the measure of the credibility of the hypothesis. And this is the particular frequentist approach. And this particular extreme probability is known as a p-value, and that's what this lecture is about. So, to sum up, the Bayesian approach provides a complete and logical solution, but it requires prior probabilities. And in particular, you can't just use arguments of symmetry. Prior distributions are things you have to think about carefully. There's a tendency, I think, sometimes to try and be automatic about Bayesian statistics, and that's not possible. And different people will come to different conclusions. You have to accept that. That's an inevitable consequence of being Bayesian if you want to be. So, some recent criticisms of p-values, which is the other approach. John Ioannidis, in 2005, published a paper entitled Why Most Research Findings Are Wrong, by which he meant why most positive research findings are wrong, why most claims that a treatment has an effect, that a particular interesting association applies or whatever, why most of these things are wrong. And he imagined a little, by the way, this has been a bit of a citation classic, 4,491 citations by the 26th of March, which is when I finalised this particular talk, according to Google Scholar. And on the right-hand side there, you have the model of Ioannidis regarding this. So, we imagine we have a hypothesis, either the alternative is true, which is that something interesting has happened, or the null hypothesis is true, it's really boring. Actually, the two treatments you investigated were identical. It just so happened that you were unlucky and you got a result that tended to suggest they weren't. So there's the null as the alternative. And he gives these a prior probability of, prior odds of R, which means the prior probability of the alternative being true is R over 1 plus R, and the prior probability of the null hypothesis being true is 1 over 1 plus R. For example, if R was set equal to 1, there'd be half a chance the alternative was true, there'd be half a chance that the null hypothesis would be true. Then he imagines that the probability of getting a positive result if the null is true is governed by alpha. Hence, the probability of getting a negative result is 1 minus alpha. The probability of getting a positive result if the alternative is true is beta. Of getting a negative result is beta, and the probability of getting a positive result is 1 minus beta, which is sometimes referred to as the power. Then he says, let's assume that what we have seen is we have seen a positive result. So he does exactly what I did in that particular table with the CD player. I simply struck out that which hadn't occurred, and then you can go through the same calculation and you calculate what the posterior probability is, and you get a true positive rate from this, and by putting in certain plausible values of alpha and beta, he comes to the conclusion that most positive findings are in fact wrong. So what you've done is you've published that wonderful paper, you claim some particular effect, in actual fact it's not true. So this brings us on to the Many Labs publication project. Here I feel a bit nervous because what I know about psychology could be written on the back of a postage stamp. But apparently there are a number of key findings in social psychology, and a very, very impressive and vigorous project was set up where a number of different laboratories throughout the world agreed to try and replicate these particular findings. And this particular diagram, which is taken from their paper published in Social Psychology in 2014, shows the situation. The original effect is given by the X on the diagram. So here's an example of some original effects. And then the follow-up effects, this is the international attempt, and this is US only. I'm not quite sure why they felt it was necessary to separate the US from the rest of the world there, but it's sort of parochial pride perhaps in what the US was doing here. And what they showed is that the results that you got the second time round were not necessarily particularly close to the results the first time around. Many people have been shocked by this diagram. I have a sort of negative, probably inappropriate prejudice against psychology. I sort of feel, well, why should any of it be true anyway? You know, that's basically my feeling. And so I actually think that this is pretty impressive. I think that the replication here was far higher than I would have expected. I'm slightly baffled as to the enormous fuss that's been, but apparently some particular psychologists have been tearing their hair. Of course, some people, these people out here, they're in a bad way because they'd actually claimed something rather impressive, and all attempts to replicate it have ended up with something less impressive. But out here, we seem to have got the reverse. We seem to have actually got some replication results that were much more impressive than the original ones. So here we are. That's the Many Labs replication project for you. Well, all of this surfaces every now and then, but recently the American Statistical Association has decided that what it needs to do is to give people advice on how to use p-values. P-values are regarded as being the principal culprit in the lack of replication that is seen in science. I don't think this is true, but anyway. And they've made a number of statements. They've said p-values can indicate how incompatible the data are with a specified statistical model, but they do not measure the probability that the study hypothesis is true. Remember what I said? The probability that the Pope is Catholic is not the same as the probability that a Catholic is the Pope. You mustn't reverse the probability here. The probability of the data given the hypothesis is not the probability of the hypothesis given the data. 3. Scientific conclusions and business or policy decisions should not be based only on whether a p-value passes a specific threshold. 4. Proper inference requires full reporting and transparency. 5. A p-value or statistical significance does not measure the size of an effect or the importance of a result. For example, if you had an extremely large study, you could get a small p-value even though the effect itself was not particularly impressive. And by itself, a p-value does not provide a good measure of evidence regarding a model or hypothesis. Now, a lot of people complain that this is really pathetic. The ASA should be much more definite about this, but I can tell you, as one of the statisticians involved in drafting the statement, there were about 25 of us, it was pretty impossible to get an agreement as to what the situation should be. And this is, by the way, this is the point at which I introduced into my talk the obligatory purloined cartoon. This is the daydream of cat herders, and the cat herder thinks, I think I'd rather manage a large software development project. So managing a large software development project is marginally better than cat herding. However, Ron Wasserstein was in charge of organising the p-value statement, and my opinion is that he probably at the end would have said, it would have been better to have been herding cats. So here we have a cat herder who says, at least I'm not in charge of the ASA p-value statement. There we are. In summary, there's been mounting criticism of null hypothesis significance testing, as it's called. Some people claim that science is broke. You will see lots of statements to this effect. The fact that things can't be replicated perfectly shows that science doesn't work. What are we going to do about it? Some people say, oh, p-values are to blame. If only we could all be Bayesians, everything would be fine. And there's a lot of advice, much of it conflicting, flying around. So, a brief history of p-values. By the way, the collective noun for statisticians is a quarrel, according to John Tukey. So it's often claimed that if you ask two statisticians about something, you get three opinions. So this is the common story. Scientists were treading a path of Bayesian virtue. Then along came a statistical diabolical figure called R.A. Fisher, and he persuaded them into the path of p-value madness. But had it not been for Fisher, then they would have naturally carried on doing the Bayesian statistics that they were doing before. And it's these p-values that are responsible for a lot of unrepeatable nonsense, and if only we could return them to the path of Bayesian virtue, then everything would be fine in the scientific garden. But the history is not like this. This is a complete misrepresentation of the history, and I think it's a good point to start with the history to understand what the problem is. So here, for example, is a quote from students, an extract from students' particular paper. Student was a statistician, W.S. Gossett, who worked for Guinness, and he was given leave of absence for 1 year to go and work at University College London, and he studied the problem of small samples in Carl Pearson's laboratory. It's not clear to us to what extent he actually ever discussed this problem with Carl Pearson, but he was there at University College London, and he came up with the t-test, which no doubt some of you have encountered during the scientific work that you've been doing. And he used an example of a particular experiment which had been carried out in the insane asylum at Kalamazoo, in which a number of inmates had been given on different nights, they'd been given certain possible soporifics. And he showed how you could analyze the difference for a given individual. You could calculate the difference between the hours of sleep under one soporific and the hours of sleep under another, and you could then apply this t-test which he just developed to this. And this is what he said. From the table, he had to go through the work of tabulating the integral and everything. From the table, the probability is 0.9985, or the odds are about 666 to 1 that 2 is the better soporific. And this statement is based upon a tail area probability. And this tail area probability is formally equivalent to the p-value. So here we have something actually quite mysterious. And in fact, I've given you a quote there of the same thing was used in R.A. Fisher's book, Statistical Methods for Research Workers, and he makes a slightly different use of it, but essentially he's using the tail area probability and he gives it a slightly different interpretation. So here we have an example where a p-value is actually given a naive inverse interpretation. It's as if students actually believe that the probability that the Pope is a Catholic is the same as the probability the Catholic is the Pope. Here he actually simply takes the tail area probability and he describes it as being a statement about the hypothesis. And we could, using a modern approach, we could say that what he did was he constructed a Bayesian posterior distribution. The peak of that particular curve there, that's the observed difference in terms of hours of sleep gained. And student then calculates what he should believe is a Bayesian, and basically he says the probability that the treatment is not a soporific after all is rather small. And this is this 666 to 1 or whatever that he quotes. So that's how student sees it. Fisher sees it a different way. He says, let's suppose the null hypothesis is true, that the treatment doesn't work. Let's suppose it's true. Then in that case, that's the mean difference we observe. This particular tail area probability is the p-value. Actually, in statistical methods for research workers, he doesn't calculate the p-value. He simply says the p-value must be less than 1%, because he calculates what the 1% value would be. He's calculated a critical value. But he's taken essentially the flipped curve. He's taken the curve centering on the null hypothesis, whereas a statistic, where a student somehow mysteriously has succeeded in producing a distribution of the parameter, the true difference in sleep, by conditioning on the data. And these are the two together. These are the two curves that you would get. One, the blue curve, is Fisher's curve for the statistic if the null hypothesis is true. The second one, the red curve, is students' distribution for the parameter on the assumption that any particular parameter value at all would be equally likely in advance of seeing the data. So he's calculated a Bayesian distribution. It just so turns out that these two particular tail area probabilities are the same. So the real history is as follows. Scientists before Fisher were using tail area probabilities, but they were giving them a fairly naive interpretation following essentially a program which had been started by Laplace. Fisher was the person who pointed out this interpretation was unsafe. He said this depends upon what you assume about the prior distribution. However, here's an interpretation which doesn't depend on what you assume about the prior distribution. It's merely a statement about the unusualness of the data if the null hypothesis is true. He also suggested a further step, which was doubling the p-value, two-tailed tests as we now call them. There's no way in which what Fisher was proposing could be presented as being less conservative than what the Bayesians were doing at that particular stage. Actually, his particular use of the p-value in this way was not the first time. You would occasionally encounter it in the writings of Carl Pearson. But it was Harold Jeffreys, sometime later, back towards the end of the 1930s, Fisher's book was from 1925, who suggested a radically different approach to Bayesian statistics. And this is worth looking at. Jeffreys was much impressed by a Cambridge philosopher called Charlie Broad. And Charlie Broad had pointed out that a particular law of succession of Laplace's could be used to show that it was quite likely that the next time a particular thing was investigated, it would turn out positive again, but it could not be used to prove scientific laws. And this is what Jeffreys has to say. What Broad showed was that it was no justification whatever for attaching even a moderate probability to a general rule. It must have a moderate probability to start with. In other words, you could not start with an uninformative prior distribution and hope to get a scientific law out of it. You had to attach a lump of probability to the law being strictly true. If you did that, you could end up with a posterior probability that the law was true. And we can argue as to whether this is important or not. It partly depends to what extent you believe in pure physics laws or not, but this is in fact what Jeffreys thought. And the key figure here is Charlie Broad, who was just a little bit older than Jeffreys, and he, in a paper in 1918, considered the following problem. You've got a number of counters in a bag, and you've drawn them all out, and all the ones which you've drawn so far have been white. The problem now is, what's the probability that they're all white? And he shows that these two things are very, very different. The probability that the next counter drawn will be white could be quite high if you've seen a large number of counters so far, and they're all white. But the probability that all future counters will be white is not high. In particular, if the number of counters that are in the bag that remain are much, much higher than the ones that you've drawn so far, the probability that they're all white can be quite low. And this, if you translate it into scientific terms, is the following. You may have seen a number of positive instances of a law so far. That doesn't mean that the law holds in general, because for the law to hold in general means you have to be able to make a statement about an infinity of future probabilistic statements. So this is what Jeffreys concluded. If you have an uninformative prior distribution, the probability of a precise hypothesis is very low. It will remain low even if you have lots of data consistent with it. You simply cannot prove scientific laws in this particular way. Now, some philosophers, the most notable example was Karl Popper, for instance, have concluded that's not a problem. There's no reason why you should be able to prove that scientific laws are true. Scientific laws are simply things that you assume are true until evidence forces you to replace them. But Jeffreys was not of this particular point of view. He really was of the point of view that induction, successively seeing particular positive occurrences, meant that you could attach a posterior probability that was higher and higher the more positive instances you saw of a law being true. You could, in fact, try and prove on the basis of having observed a particular law in the past that it was true in some way, or probably true. You need to allocate a solid lump of probability that it's true. You need to have a finite lump of probability on the law being strictly true. You can't simply smear it everywhere. In students' use in the t-test, he would simply have smeared every possible effect of the soporific, every possible true effect he would assume was equally likely over a very, very, very large range, and then on that basis he gets his particular tail area probability. So, here's an example, simulating just for fun. These days people seem to believe simulations more than theory. So I've simulated just for fun. I've simulated two particular cases, and what I've done is I have calculated, using my simulation, a sort of Bayesian posterior probability, and I've considered two particular cases. One is that what I've started with is a smooth prior probability, and I'm testing here a dividing hypothesis. I do a lot of work in consulting for the pharmaceutical industry, and I've said, supposing we just want to know the difference between a drug being useless or harmful or beneficial. I'm just going to argue a priori that every possible value of the effect of the drug, from being extremely harmful to being toxic to being a wonderful elixir of life, each of these prior probabilities is equally likely. I'm going to simulate from that particular setup, and I simply want to know whether the effect is positive or not. Then in that case, this is the one-sided p-value, by the way, I plot on the right-hand axis, on the x-axis. On the vertical axis, I calculate the false positive rate, and these two things agree. That's the line of exact equality, and the red line simulating, bearing in mind that simulation is bound to be some difference, no difference. I can interpret the p-value under those circumstances as a posterior probability, and this is indeed exactly what student was doing. It follows from that particular approach of student. If, on the other hand, what I do is I attach a lump of probability to the null hypothesis being true, to the drug being useless, but I have zero probability on the drug being harmful, none whatsoever, then this is the particular situation that arises, and you get a very dramatic departure of one from the other. So my point here is the conflict is not between Bayesian statistics and frequentist statistics per se. And if you go back in time and you see that in a sense Fisher, the frequentist, was agreeing as regards the numerical values assigned with student, the disagreement is between two particular Bayesian approaches, but these are not the only two, there's an infinity of them. There's no particular reasons why they should agree at all. And so actually you'll find that what we have at the moment is, and this is my title, P-value wars, we have a war in which it seems that naive frequentist analysis is being attacked vigorously by Bayesians, but it's really a cover for something else. It's really a fight between two particular Bayesian points of view. And if you look at the ASA statement, you'll find there were some Bayesians who were adamant that testing a precise null hypothesis was a very important thing to do, and there were others who were of the opinion that it was absolutely of no importance whatsoever. So, for example, Rod Little was of the opinion that there was absolutely no value whatsoever assigned to testing the idea that a null hypothesis was true. As far as he was concerned, everything was estimation, and this was just a silly idea. On the other hand, if you look at Jim Berger, then he is of the opinion that that's the most important thing you could be doing would be actually testing a precise null hypothesis. So why the difference? Well, imagine a point estimate of two standard errors. Now consider the likelihood ratio for a given value of the parameter delta under the alternative one of the null. If you have a dividing hypothesis, what I can do is I can match any positive value of delta with the corresponding negative value of delta. And provided my distribution is symmetrical about 0, my prior distribution, each of these two values has identical prior probability. Now the positive one has much bigger support from the data because the data were in the positive area. And the negative one has much less support. And so for every single pair of values under the alternative and under the null that I put together, there's always more support for the one under the alternative. On the other hand, if I have a point null hypothesis, this is not true. What I then have is I have a jar of infinite values of delta equal to 0. There are as many of them as I like, and every positive value of delta can be matched with a value delta equal to 0, and some of these positive values will be given much less support. Supposing it's the case that the effect of the drug is to increase your forced expiratory volume in 1 second by 100 milliliters. At least that's what I've observed. I've observed that. Now, one of the values under my alternative hypothesis says, oh, it could actually increase it by half a litre. But half a litre is further from 100 milliliters than 0 is. And 0 is a value under the null. And so actually what I end up having is I end up having less support for the alternative hypothesis, even though I have a positive value, than for the null. And this is a consequence of Jeffreys using a lump 0. In summary, the major disagreement between p-values and Bayes is not between p-values and Bayes, where Bayes uses an uninformative, that should be an uninformative prior distribution, rather than informative, misprint there. It's between two Bayesian approaches, using uninformative prior distributions and using a highly informative one. So this conflict is not going to go away by banning p-values. That might not be a bad thing, because one might then say, well, you know, once we can clear these terribly old-fashioned and stupid frequentists out the way, then in that case the grown-up Bayesians can have a proper fight about what it really should be about, which is how one chooses one's prior distributions. In the meantime, this distraction of this frequentist approach is getting in the way. But the point I make here is there's no such thing as automatic Bayesianism. You have to do it for real. It really does require you really thinking very carefully about what a prior distribution is, and there's no such, in my opinion, there are no serious cases in which default priors will give you reasonable answers. Conclusion, statistics is difficult and statisticians should be paid more, by the way. What you should know, however, P equals 0.05 is a very weak standard of evidence. In actual fact, two-tailed, one could say that the maximum value of the likelihood under the alternative is only 6 times what it is under the null. It's not a strong standard of evidence at all. You should regard it as being at most, at best, worth another look. You certainly should not regard a significant result that you have at the 5% level from a single study as being indicative that there's something there. In fact, the FDA doesn't accept it. The FDA will require you to produce 2 phase 3 trials, each of which is significant at the 5% level. And of course, to get there, you must have screened a lot of molecules in preclinical. You must have tested them in vitro. You must have tested them in phase 1, phase 2A, phase 2B studies. So you don't arrive at phase 3 with candidates for treatment which are unpromising in the first place. If you were to replace the FDA's 2 trials requirement by a single trial, you'd be looking for something like a p-value equal to 1/800, two-sided. Variation in results from trial to trial is natural, by the way. Another mistake that people make is they imagine that you should be capable of repeating a significant result. But if the result is just significant, even if the effect was actually true and equal to the value that you estimated, then half the time you get a statistic which was slightly below the value sought, in which case it would be non-significant, and half the time above. So something like a 50% probability of replication would be reasonable, rather than something like a 90% that people seem to think will be appropriate. As far as if you're a Bayesian, it's not what another trial would show that's important to you, it's what another trial of infinite size would show that is important, because you're saying something about the true situation. Don't just rely on p-values. Bayes is harder to do than many people think, and pay attention to the ASA advice. So these are the solid 6. I'm not going to go through those again. But I'm just going to quote this particular statement from 2 psychologists looking at this, published a paper in 2015. They say proponents of the Bayesian revolution should be wary of chasing yet another chimera, an apparently universal inference procedure. A better path would promote both an understanding of the various devices in the statistical toolbox and informed judgment to select among these. Thank you very much.
So we would now have time for questions, if there are any immediate questions, and later we will have the open discussion then as well, if people have any questions. Alison?
I'm afraid. Well, I'm not afraid. I was following perfectly well, I think, till slide 37, and then I got a little bit lost about exactly what you were saying about that. And I understood the summary, but I didn't understand, yes, kind of just the bit before that and then this bit. Sorry.
Okay.
If you could explain that in a slightly different way, or with an example.
I can use the board here, maybe.
If it, we can all walk up to it left where I can.
Well, let's imagine that you have Jeffrey's case with a lump of probability here. And that's essentially the likelihood under the null. So a lump of probability here, that's the prior distribution. And now what you have is you have the prior distribution under the alternative hypothesis, and it'd be something like this, stretching out to here. And the question then would be, and this could be fairly wide, and this is essentially the setup that you have. In the other case, where you have an uninformative prior, incredibly flat distribution like this for the prior value. Now, if you have a look at the likelihood under the particular case we're looking at, the likelihood will be something like this. The maximum value of the likelihood will be at the observed statistic, which I said was 2 standard errors, something like that. And it will stretch away as I get further away from that, as I get up. So this is the value of tau equal to the statistic. The highest value of the likelihood will be exactly where the prior parameter value is equal to the statistic that you see. The most supported value, if I have a difference of 100 milliliters in blood pressure, the most supported value is a true difference of 100 milliliters. Out here, in this particular area, I'm going to have a large number of unsupported values. If I see a difference of 100 milliliters, let's say, in FEV1, then it's less less well supported that the true difference is 200 milliliters, so on and so forth. As I get right out to the positive area here, then it's less and less supported. However, if the prior distribution is like this, every single positive value can be matched to a negative one, which is even less well supported. If it is unlikely, if the result is unlikely, if the true difference in 4-6 Friedrich volume is 500 milliliters, it's even less likely if the difference is minus 500 milliliters. So when I have a continuous distribution like this, I find that all the values that are not in the alternative hypothesis are even less well supported than the value that I have. Not so here. Because here, if I actually observe a value which is down here, right, well, okay, it's actually quite well supported by 0. It's not that far away from the value I was, that's the value, that's the likelihood at 0. It's not that far away. Okay, anything up to, let's say, 200 milliliters is equally well supported in the alternative hypothesis, but the values out here, I'm going to match them to something which is acting to 0. So they're much, much less well supported. So this is essentially what happens, is you find that you've got lots and lots of candidate values under the null hypothesis which are better supported than the one of the alternative if you have a lump of probability on it. If it's smooth in either direction, that's not the case. So the irony is the following. If you believe that the drug could be toxic, if not beneficial, you end up thinking it must be beneficial. If you believe it's harmless, if not beneficial, you end up believing it's harmless. Okay, so it's difficult. I've not explained that very well, but I have a blog post on this. It's no.
Any other questions for now? Not. We could meet here again at 4:04, and we have now coffee and biscuits in the foyer. And then we will resume with Michael's talk, and after that, the open discussion.